All right. Thanks for coming to this week's UTIG discussion hour. This week we have UTIG's own Kirk Scanlan. He is a postdoctoral fellow here at UTIG. Before coming here, he received his PhD in geotechnical engineering from the University of Alberta, a master's via the Idea League, and his bachelor's of science from the University of Western Ontario. Kirk is a member of the Reason Science team, which is an ice penetrating radar that will be on board the Clipper mission to Jupiter's Europa, Jupiter's moon Europa. And so today he's going to talk to us about using Reason to investigate plumes on Europa. So take it away, Kirk.
Thanks, Naoma, and hopefully everybody can see my mouse as I'm moving it around. And thanks for giving me the opportunity to talk to you all today. Hopefully it won't take too long. And if anybody has any questions, just feel free to pipe up and interrupt me as we're going through. Before we head into outer space, I just wanted to start with a land acknowledgement. And I'm going to envision everybody sitting around my desk, which is also my kitchen table in my apartment. And I would just like to acknowledge that we are meeting on the indigenous lands of Turtle Island, the ancestral name for what is now North America. Moreover, I'd like to acknowledge the Alabama Coshada, Caddo, Carrizo, Comecrudo, Coahuiltecan, Comanche, Kickapoo, Lipan Apache, Tonkawa, and Isleta del Sur Pueblo, and all the American Indian and indigenous peoples and communities who have been or have become a part of these lands and territories in Texas. So moving on. So now we'll move in to talk about Europa. I think most people who I saw on the participant screen on this call may already be familiar with a little bit about Europa, but for those who are not, a little bit of background. So it's the second Galilean moon of Jupiter, first observed in 1610. It was the least studied Galilean moon by Voyager 1 and Voyager 2, but it was the target of Galileo's first extended mission. And from those Galileo measurements, we were able to discern that Europa has a putative global ocean under an icy shell. So this is just a cutaway. We have the core, rocky mantle, and then this hydrosphere, say 100 kilometers or more or less thick. We have a water ocean underneath this ice shell of indeterminate thickness. And it's really interesting and exciting body, but we only have limited data from Galileo. So what we have to do next is send another spacecraft. So, whoops, went one slide too far. So this is Europa Clipper. It's a little bit of an out of date look at what the spacecraft looks like, which just gives kind of the general dimensions of it. Europa Clipper is scheduled to be launched in October 2024, has a 6-year cruise till Jupiter orbital insertion, has a 4-year science phase, and has 9 different science instruments. So we have cameras, imaging spectrometers, mass spectrometers, dust analyzers, magnetometers. But what I'm most interested in, and what UTIG is primarily responsible for, is the Reason instrument. So you can see these Reason antennas hanging below below the solar panels. Reason is the radar for Europa assessment and sounding, ocean to near surface. And as you can tell from the picture, it's a nadir-pointed dual frequency instrument. We have a VHF channel operating at 60 megahertz and an HF channel operating at 9 megahertz. A little bit of background on what Reason hopes to accomplish. We have 5 science objectives listed here: investigate Europa's subsurface ocean, measure the ice shell thickness, improve our understanding of ice shell structure, study the elevation, composition, and roughness of Europa's surface, and search Europa's atmosphere for indications of plume activity. And since I'm going to use this talk to talk about plumes, we'll talk a little bit about how they fit in. And I see them fitting in 2 main ways. So first, kind of in this 4th objective, when we're looking at the surface, we can use Reason to look for and study plume fault deposits preserved on Europa's surface. And then kind of obviously from the 5th objective, we're going to use it to search for indications of plume activity, and we're going to do that through the electron density anomalies in Europa's ionosphere. And these are kind of the 2 main thrusts of my talk today. Just going to go through some ongoing work on each one of these topics. But before we get into one last thing before we get into these in detail is just what kind of observations already exist for plumes on Europa. And So there have been a couple different lines of evidence for Europa plume activity, and mainly they come from Earth-based telescope observations and reanalyzed Galileo measurements. So this map on the lower left, I'm just summarizing kind of these 7 papers. We're looking at different plume detections at Europa. The green, blue, red, and yellow areas, these are from Earth-based telescopes. So the first 3, I believe, are Hubble Space Telescope observations. This yellow one is a Keck infrared observation, so mostly made from Earth. And these, the kind of pink star and the light, or pink triangle, sorry, and the light blue triangle, those are hypothesized plume locations based on the reanalysis of Galileo magnetometer and plasma measurements. And what's really interesting about this, about Europa plumes, is that they're very much not ubiquitous. They're not everywhere. And you have to, some of these Hubble Space Telescope observations, they were looking for these for months and months and months on different days of the month, even across years. And they maybe come out with 1, possibly 2 different observations. So when we think about plumes on Europa, it's not something that we'd see on Enceladus. Like, this is a Cassini photo of Enceladus and the South Pole of Enceladus, and you see these giant jets of plume material that are constantly erupting from the South Pole and the Tiger Stripe area. That is definitely not what we're expecting to see at Europa, where the plumes are much more ephemeral. So now I'm going to dive into the first part of my talk, and I'm going to describe how one way I envision reason being used to look at plume fallout deposits preserved on Europa's surface. So there is some evidence that has been hypothesized for plume deposits preserved on Europa's surface, and these come from Galileo imagery. And they're often these described as smooth and low albedo areas. So these are just 2 pictures that I've pulled out of the literature, and kind of these smoother areas on the flanks of this double ridge, or what I think is a little bit more easier to wrap your head around is kind of this area here. We have this ridge terrain that's just been blanketed and covered by this kind of darker, low albedo material with this kind of circular shape, which is, if you were expecting you had some kind of plume erupting on the surface, that's kind of the depositional pattern you would expect to see. So if we want to start talking about how we can use reason to study plume deposits preserved on Europa's surface, we have to start with a plume depositional model. So the model I've implemented is adapted from Lene Quick and Matt Hedman's 2020 paper, and it considers 2 families of water-dominated plumes. So we have water vapor as the main gas phase of the plume, and then water ice grains as the solid component of the plume. And it's the fallback of those solid components that are generating these deposits. And the particle radii that are assumed in the model vary between 0.5 to 3 micrometers. So for low altitude plumes, generally classified as those with the heights less than 25 kilometers, they just use 3 examples, so 1 and 10 and a 25 kilometer tall plume. And what's unique about these low altitude plumes is that all particles that are erupting from the plume vent are suspended in the water vapor phase. So they're all traveling with the same velocity. And that has important implications for the depositional rate. For the high altitude plumes, those greater than 50 kilometers, so the 4 examples that are used in this Quick and Hedman paper are 50, 100, 200, 300 kilometer tall plumes. And there we have eruption velocities that are particle size dependent, which again plays an important role on the depositional rates and how the material is deposited around the plume vent. So this is just a summary of the parameters that are fed into the plume deposition model. They're not terribly important. The only reason I have them in here is just to show that these numbers are calibrated to a Hubble Space Telescope observation. So it's not like we've had to pull numbers and just make up numbers. This is an actual number that is inferred from a Hubble Space Telescope measurement or something that may exist at Europa. So they're not unrealistic numbers. So then we take those numbers and we feed them into the plume eruption model, and then I calculate depositional rates for each plume. And we've used two different constant porosities for the fallout deposit. So we have a porosity of 0.5, which is kind of your closest packing of spheres. It's meant to represent an old plume deposit that has undergone some kind of densification on the surface with time. And then we have a kind of a porous deposit, so this N of 0.9, which is meant to represent a fresh deposit, so like freshly fallen snow. And just note that the porous deposit accumulates with about an order of magnitude greater depositional rate than the denser one. And we can see for low altitude plumes, so 1, 10, and 25 kilometers, because every particle is ejected from the plume at the same velocity, we have these constant depositional rates as a function of radius from the plume vent. And because the model assumes a ballistic trajectory, that maximum depositional radius, so these points where these stop, is twice the plume height. So for a 25-kilometer plume, the maximum down range, it's going to deposit some material is 50 kilometers. For 10, it's 20, and for 1, it's 2. That's just an implication of how the model is defined. For high altitude plumes, because we see that variable or grain sign dependent depositional rate, we no longer see these sharp cutoffs. We see these more flanked gradients until you get your smallest. You have your smallest grains are deposited at your further away from the plume vent, with your larger grains deposited closer. So you get these nice smooth flank deposits. And then we can put them all together, and these are the 7 plumes with 7 different plumes, 14 different deposits with different sets of porosities for the actual deposits themselves. So then what I'm going to show next are, okay, wait, sorry, I got ahead of myself. So now that we have our plume depositional model, we have to figure out a way to understand how the radar will interact with these types of deposits. And what I've done is I've applied a radar reflectivity model adapted from the studies of the Martian southern polar caps using MARSIS. It's a pretty simple 3-layer model. We have a half space comprised of vacuum, a half space comprised of water ice, and then we have some intermediate layer of finite thickness that represents our plume fallout deposit with different permittivities depending on the porosity of that layer. And then we can vary this thickness by looking at the depositional rate and how long we assume the plume was active for. Fit that all into this equation here, and you get a integrated surface radar reflectivity for that 3-layer stack. If you do that just as a parameter sweep over a range of fallout deposit thicknesses, these are kind of the results. We have the recent VHF measurements for the 2 deposit porosities in red and recent HF measurements in green. RIME is here for completeness. RIME is the radar sounder on ESA's JUICE mission, but I'm not really going to talk about RIME today. And just a couple of things to point out from this model that will become important on the next few slides is the reason VHF has a higher range resolution, so it's more sensitive to small changes in plume fallout deposit thickness as opposed to the HF, which has a lower range resolution. And what I do in the model is once the thickness of that intermediate fallout deposit exceeds the range resolution of the radar, I no longer consider this a 3-layer problem, and it just collapses to a half space, for the surface echo at least, a half space of vacuum and the plume fallout deposit. So that's what these big drops are in reflectivity, and that's just where it collapses to a constant level as a function of deposit thickness. That's just where the range resolution is less than the thickness of that layer, of that intermediate layer. So you should be able to resolve the top interface and the bottom interface separately. And then the last thing I want to point out is just some general reflectivity patterns. So for the dense plume deposit, there's a lot of oscillation kind of around a mean level of say minus 16 dB. And this minus 16 is roughly the reflectivity for just between vacuum and a dense plume fallout deposit, irrespective of the water ice below. But we see for the porous plume deposit that the reflectivity is much more dominated by this lower interface between the deposit and the water ice, just because this contrast between the vacuum and the fallout deposit isn't very big. permittivity of 1 to a permittivity of 1.16. So once this deposit hits that range, exceeds the range resolution, you get a very steep drop in reflectivity just due to this much weaker permittivity contrast. So now that we have our depositional model and the reflectivity model, we can put these together and start looking at some actual patterns through space and time for different plumes. So what I've done here, I just have 4 kind of example movies. So this is for a 25-kilometer tall plume that's producing a dense follow deposit. And I'll just play it and we'll talk as it goes. So as we mentioned, for a 25-kilometer plume, we have these constant depositional rates. So that's what's shown here. You just see one kind of spot in the middle that's oscillating back and forth in terms of reflectivity as there's constructive and destructive interference set up within the fault deposit itself. You can see the VHF starts oscillating it oscillates much quicker than the HF just because it is more sensitive to smaller changes in thickness. The HF is also oscillating, but much slower. Eventually, the VHF will hit that range the fault deposit will exceed the range resolution of recent's VHF, and then it'll stop oscillating. So I think it's about 380 odd years. So just about, yeah, you can see it just stopped changing. So that's when it's hit the range resolution. And now it's just a constant value because it no longer sees that bottom interface. Whereas the HF will change all the way up to 500 years, after 500 years of our activity. So we can do the same thing. Oh, and I should mention that all these plots have the exact same color bar. So red is a high reflectivity, blue is low reflectivity, and they're all over the same scale. So they're directly comparable to one another. So this is for the same 25-kilometer plume, but now we're depositing a porous deposit. You can see we're gonna oscillate much more quickly in the VHF, but not as deeply. So there's quicker oscillation, but it doesn't get the same kind of variability as we saw for the lighter plume or the denser plume deposit. And again, it's going to hit that range resolution limit much earlier in its lifetime just because it is depositing much quicker. So before we hit that range resolution after 380 years, and now we hit it after 80 years. So just because it's growing so much quicker, it's hitting that. And the HF is still just plugging along by itself, oscillating back and forth, even after 500 years. So now we're going to go to a 200-kilometer tall plume. So now we're in that kind of grain size dependent deposition rate and a denser deposit. And it's going to look a little bit different. So what we actually see here are these ripples in reflectivity that spread out radially as a function of time for both the VHF and the HF. You see the interior portion is still exhibiting that oscillation that we saw for those constant deposits. But because that thickness is, because the plume deposit is accumulating over a greater area and at different rates, it's actually, you're seeing a much more interesting spatial structure. And you can just ignore this little, there's some, they should be perfect circles. This little part over here is just a plotting error, just how the data are plotted up together. So yeah, I just think they're kind of hypnotic to look at almost. And for the last example is a 200-kilometer tall plume with a porosity of 0.9, so that light, fresh snow. And what's going to happen here, we're going to see these ripples. Again, they're going to spread out faster, but because the reflectivity is more dominated by that follow deposit water ice interface, the ripples aren't as deep. And again, we're going to hit that range resolution limit much earlier in the life cycle of the plume deposits. After only 25 years, the VHF has already hit that resolution limit, and the HF hits it pretty early as well. And then these ripples just spread out through time, and the area that exceeds that range resolution also spreads out through time. So kind of looking at these, if we do see some kind of pattern that would be indicative or maybe diagnostic of a plume deposit on Europa's surface with reason, because we have the VHF and the HF, we can actually do some pretty interesting things. And that's why it's important to have two frequencies, is we can back out some of the properties of the plume that drove those deposits. So we can actually look backwards in time for the dynamics of Europa's ice shell, just by how these deposits are preserved on the surface. So for short plumes, those less than 25 kilometers, eruption timescales can be inferred from a joint analysis of the VHF and the HF. We only have to concern ourselves with timescales just because the radial extent of these deposits are directly related to plume height by the ballistic assumption in the model. However, for tall plumes, we have to be able to characterize both eruption timescales and plume heights because the depositional rates vary. There's no one-to-one correlation between, I'm only going to see this thick of a deposit from this plume at this specific distance from the vent. But it's still possible to do it from joint analysis of the VHF and HF measurements. And how I see this, one way to do this that I envision would be to look at the position of this outermost ripple, because this ripple is actually this trough in reflectivity actually corresponds to a frequency dependent deposit thickness. So where this blue annulus sits is a specific thickness related to that driving plume. So for the VHF, it's about 0.5 meter. For a dense plume deposit, for a porous plume deposit, it's about 1.16 meters. And this is just the point of where maximum destructive interference is reached. For the HF, it's much greater just because the vertical resolution of the HF is less. So then if we plot the position of that trough in reflectivity as a function of length of plume eruption in years and the different plume heights, we could generate these kind of diagnostic curves for the different plume porosities. So you could envision if I see something in reason data that would imply that I have a trough in reflectivity that's 60 kilometers from my plume vent, just by looking at the VHF data, so these solid lines, it'd be really hard to nail down exactly how long that plume was active for or its height, because depending on its height, it could be active for a different amount of time. A 200 kilometer tall plume could build up that thickness in 40 years, or a 50 kilometer tall plume could build up that thickness in 500 years. But if we also had the VHF and we were able to go, okay, I see an equivalent, I see another minimum in HF reflectivity at 30 kilometers, you can almost guarantee, you could really nail down and resolve that. Okay, that's a 200 kilometer tall plume that was active for 40 years that emplaced that deposit. And you can do the same thing for the higher porosity deposit. The only caveat is that the plume has to be active for a long enough time to emplace that thickness. So you can see there is a minimum length of time to generate a deposit of the requisite thickness for both the VHF and the HF. And obviously it's quicker for the VHF. But there's less time required to emplace a thinner VHF layer than it is to emplace the thicker HF layer. So to sum up this, the first part of my talk, just talking about the plume fault deposits, they represent a window into understanding the past activity levels within Europa's ice shell. And because Europa is such a young surface, there's not many craters, there's not much active resurfacing going on. These type of deposits may be well preserved today, so we can go back and look backwards through time. And that region is well suited to detect and characterize these plume fault deposits through the joint analysis of VHF and HF measurements. However, the model we've used, or the model I've used to generate these reflectivities is pretty simple, and there's a lot of other factors that can conspire together to complicate this type of analysis. So we expect the plume fault deposits to be smooth on their surface, but as we saw in the Galileo images, they do fill in and overlie a lot of topography. So how that buried surface roughness impacts the reflectivity is not constrained at all in the model. We can also have porosity variations in the buried surface. So this analysis so far has just been based on solid water ice under the deposit, but that ice is actually probably porous and fractured, so that will change how the degree of constructive and destructive interference. And then we also have to deal with the fact that we have broad reason footprints, if we have up to 10 kilometers in diameter. That will also, we're not just looking at a single point to characterize thickness. So that ends the first part of my talk, and now I want to, where we looked at like plume deposits preserved on the surface from a plume that happened before we started looking. Now I want to talk about how reason can contribute to actual plumes that were flying through or flying over as part of during individual Europa Clipper flybys. So I guess the first question most people have when you think of radar, you think of, oh, I can look at the surface, I can look below the surface, is how is a radar sensitive to an ionosphere? And radar wave velocities are a function of dielectric permittivity. It's something we know. It holds in the subsurface, but it also holds for an ionosphere. And in the typical subsurface, permittivity is typically a function of material type and density, or as we saw in the first part of this talk, porosity. However, when we start propagating radar waves through a charged plasma, so an ionosphere, those radar waves actually interact with the electrons and can be either slowed or completely dissipated just due to that interaction. And what's important is that these ionospheric dispersion effects are frequency dependent. And this is something there's a lot of heritage with from using radar sounders on Mars. So this is just an example of Martian ionospheric dispersion. So on the top, we have an uncorrected charade radargram of the Martian northern polar caps. You can see how all these reflections are smeared and defocused, and that's just because of the phase dispersion across the charade bandwidth due to the Martian ionosphere. Now, it's pretty straightforward to correct for that on Mars. You kind of refocus everything and you produce an image that's much more interpretable and much more nice to look at. How we expect to do that for plumes on Europa or just the Europa ionosphere as by itself is through a joint analysis of travel time delays between the reason VHF and HF signals, because due to that ionospheric dispersion, they will propagate at different velocities. And this is something we've already, a framework for this has already been established from work we did on Mars, using MARSIS on Mars Express and the Charade instrument on Mars Reconnaissance Orbiter. Because they operate at different frequencies, you can do a similar kind of analysis to characterize the ionosphere of Mars. And then we're going to be looking for localized differences in this effective travel time to the surface. And those would be useful to, those would then represent what could be considered anomalies due to plumes. So when we want to understand what plumes will look like from reason's perspective, and we want to model their influence, we have to actually take 2 steps back and start with what is Europa's neutral atmosphere? Because then we'll have to ionize that atmosphere, and then we can see how reason will interact with that ionized plasma. So what I've done for modeling Europa's neutral atmosphere is just assume that the neutral atmosphere, as well as the plume gas, are dominated by molecular oxygen. So this is just one model from Rubin et al. 2015 for the background molecular oxygen atmosphere. So this is just O2 density. These coordinates on here, or these degrees, aren't representative of European longitudes or anything, or not latitudes. They're just kind of internal to the model. But for those of you who are familiar with Europa, if you were looking down on the North Pole, 0 degrees longitude would be at 270. So Jupiter is this way, and the Io Plasma Taurus is coming from this way, coming from the right. And you can see there's a slight increase in molecular oxygen density on the trailing hemisphere. So this side is the trailing hemisphere, just because it is a sputtered molecular oxygen model. So the Io Plasma Taurus is sputtering more material off of the surface, leading to this localized increase in molecular oxygen density. So we have this background neutral exosphere. We can add a plume model to that. So this is just a plume model taken from G et al. 2018. So this is just the molecular oxygen density associated with the plume. We add these 2 together, and there we have our total exosphere molecular oxygen density. So this is our kind of nominal background case for what the European atmosphere looks like with the plume in it. Then we can take that and ionize it to produce an ionosphere. I've considered 2 possible options for the rate at which the neutral exosphere is ionized to produce an ionosphere. The first is kind of a literature standard one. It's just assuming a constant ionization rate that is independent of distance from Europa's surface. It was used in this Rubin study, the G et al. 2018 study. This is the G et al. 2018 study is one of those reanalysis of the Galileo magnetometers data sets where they found a where they said some magnetic anomaly could only be due to a plume. And the second option is one that I've kind of put together, and it's a variable altitude dependent ionization rate that reproduces the electron densities that were reported from Galileo occultations. And it just assumes that neutral molecular oxygen exosphere as the base, and then matches that with Galileo occultations. And what's important to note is that because I have to do this I have to do my own kind of ionization rate, it's because the constant ionization rates that are used in the Rubin et al. 2015 paper and the Gia paper can't actually reproduce the electron densities that were reported from Galileo occultations. So there is this tension between the models that are used to reanalyze some of the Galileo data, but those models can't actually reproduce the observations that were made by Galileo. So a little bit more detail on these ionization rates. So just first is the constant ionization rate. There's two different ways you can ionize molecular oxygen. There's path 1 and path 2. And generally path 2 ionization is about 10% that of path 1. And these are the ionization rates that are usually used in the literature. So for that variable ionization rate, what I did is I took that same molecular oxygen densities from that sputtered model, from that Cassidy et al. Model, which are presented in these dotted lines. And then these kind of gray box is the range of electron densities that were reported from Galileo occultations. And then just calculating the ionization rate as the electron density divided by the oxygen density. So when you do that, these are the type of ionization rate curves you get for just different levels of electron density. For different levels of electron densities, as reported in that Cleor paper, you have kind of a high, medium, and low ionosphere. And this is path 1 ionization rates. This is path 2 ionization rate, which is just 10% of path 1. But what's interesting to note is that these ionization rates in terms of electrons per second are like 5 to 6 orders of magnitude greater to reproduce the actual Galileo data than what is usually used in models. And this has then important implications for the electron densities in your ionosphere, which are shown here. So on the left, we have a constant ionization rate produces this kind of electron density distribution, whereas that variable ionization rate produces a much denser ionosphere with more electrons in it. And so this will have important implications for how reason interacts with these two n-member ionospheres. So once we have the ionosphere, we can start calculating some of the parameters to describe how reason interacts with it. Ionospheric models are used to define two characteristic frequencies. The first is a plasma frequency, which is related to local plasma or electron density, and a collision frequency, which is related to the local neutral density and electron temperature. And then we take those plasma collision frequencies combined with signal frequencies across the reason bandwidths to define an ionospheric refractive index. So reason VHF has a 10 megahertz bandwidth between 55 and 65 megahertz, and HF has a 1 megahertz bandwidth between 8.5 and 9.5 megahertz. Then we use that refractive index and ionospheric frequencies to define expected signal attenuations and dispersive delays, so both group and phase delays. Phase delays are just calculated as the relative delay between the two ends of the different bandwidths. So we're going to start by looking at two-way attenuation. So this is just for a constant ionization rate. We have the HF on the left and the VHF on the right. And for that constant ionization rate, you can see there's no attenuation due to the European ionosphere. Like all these numbers are incredibly small, even when expressed in dB. So it's not important. For the variable ionization rate, for the VHF, again, we have no important amount of attenuation. But for the HF, you can actually see when we start looking right down the center of the plume. So if you're looking right down on it, you can get up to 5 to 6 dB of attenuation just due to the local increase in electron density if this model were to exist in reality. Now looking at dispersion effects. So here you have the VHF. We have group delay on the left, phase delay on the right. This is for constant ionization rate, all presented in seconds. So you can see for this constant ionization rate, there's almost no delay in the VHF data. So it's a microsecond at 10 to the minus 6, millisecond at 10 to the minus 3, and these are all blue for both group and phase delays. When we start talking about the variable ionization rate, kind of this background level, we're in the microsecond range for group delays. But in the vicinity of the plume, we can start getting into, say, sub-millisecond group delays associated with the localized increase in electron densities. For the HF, same thing, constant ionization rate. Again, nothing terribly unexpected in the range of, say, tens of microseconds of delay when you're looking right down the plume axis. But everywhere else, it's fairly negligible. But for that variable ionization rate, now things are starting to get a little bit more interesting. We can get up to, say, tens of microseconds in the constant background. But when you're in the vicinity of the plume, you can start getting group delays up into the tens of milliseconds, which is starting to get important for measuring these things with reason. And then what we can also do, that was kind of taking a holistic view of the ionosphere as a whole. We can actually start putting flybys through that ionosphere and see how these delays or attenuations evolve through different flybys and different trajectories. So what I've shown here is just the background map is just the electron densities associated with that variable ionization rate. And then I've just taken a couple of straight line flybys through that ionosphere, going from 1,000 kilometers to 1,000 kilometers with a 50-kilometer closest approach, and just changing the position of that closest approach or rotating it around Europa to see what the effect of the plume is. And here I'm just going to show the results from going from 70 degrees, so this position here, the closest approach is right about here, to this orientation where closest approach is now centered directly over this hypothetical plume at 20 degrees south, or 20 degrees, not 20 degrees south, at 20 degrees or kind of 340 degrees. So that's what's shown here. This is your general altitude profile across a flyby, started at 1,000 kilometers, comes zooming in, 50 kilometers at closest approach, zooming out to 1,000 kilometers. And then this is just the HF group delay as a function of ground track distance, starting from 70 and going to 340 degrees. And what's interesting, what I think is really interesting, is that when your closest approach is centered over the plume, it has its weakest visible response in the REASON dataset. And that's because REASON, it's kind of counterintuitive, but REASON is responding to the integrated electron density across the line of sight, across the radar propagation path. So when you're close to the plume, you actually don't have as many electrons between the spacecraft and the surface. So the response is actually muted. Once you get about 50 degrees away from it, so now you're coming through the plume area at your highest altitude, that's when you actually have your greatest quantity of electrons between the spacecraft and the surface. And that's when it's going to present with its most obvious signal. So just to wrap up for the second half of the talk, and I guess the talk in general. So REASON is sensitive to active plumes by way of local anomalies in ionosphere electron density, and that capability is tied directly to the dual frequency design of REASON. So if there's one takeaway for a lot of what I've talked about today, is you really need both frequencies with REASON to do a lot of work related to plumes. The current assessment of Europa plume impacts is highly dependent on the background atmosphere model and the ionization rates we choose. So, and there's there's some published Europa ionosphere models that are used to reanalyze certain Galileo measurements don't actually match other Galileo measurements. There still is that tension within the literature and something that needs to be resolved. And the next steps for this specific study should be to include some magnetohydrodynamic modeling of the impacts of the Io plasma torus. So the Io plasma torus is this kind of donut-shaped flow of charged particles that are trapped in the Jovian magnetic field that are constantly bombarding Europa's trailing hemisphere. And we have flowing charged particles interacting with a charged ionosphere, they're going to produce some kind of distortion effects. And that, just to kind of illustrate that, so this is pulled from the supplemental material in the Viet 2018 paper. And we have in A and C are models without the plume, and B and D for models with the plume. We have molecular oxygen densities on the top and just velocities on, or flow velocities on the bottom. And what you can see is when you start doing these magnetohydrodynamic modeling, you can see this wake of in the European ionosphere. So contrary to what we were showing before, now the Ioplasmatorus is coming in from the left. So this is the trailing hemisphere, this is the leading hemisphere. And you can see how it blows the, deforms the atmosphere around Europa. And a plume will have the same thing. It'll start to have this nice long tail as the plasma flows around Europa. And then this will have important implications for what the ionosphere looks like that need to be considered when we actually start talking about these things in reality. So that's it for me. Thank you all for listening. And if there are any questions, I hope I can answer them. So yeah, thanks.
So we can take questions, but there's also a couple in the chat if we want to get started with those. Cyril says, would the VHF or HF reflectivity ratio be a useful observable? Would the VHF-HF reflectivity ratio be a useful observable to further constrain the plume characteristics related to its depositional pattern?
I think, of course. Yeah, if you do the ratio versus compare them individually, you're kind of getting at the same thing, the relative proportion of each one. Yeah, I think that'd be a great way to look at it as well. So yeah, something to look at further if I want, yeah, it'd be worthwhile. But then you also have to get into the account that these are looking at different footprints. So what's effective, the surface echo you're effectively getting isn't quite comparable between the two of them. So that might also have to be adjusted for or incorporated somehow.
Awesome. It looks like Duncan has a question. Let's go to a live question. We can always come back to these questions from the chat that Sarah left.
Yeah, just following up on that. In terms of looking at the plumes and the fact that the VHF and the HF have these very different footprint dimensions, is the kind of the reflectometry approach that Cyril was talking about in the Friday lecture the right way to go, or maybe using some kind of focusing or processing to get comparable resolutions, at least for across these features, might be more appropriate?
Yeah, that's an interesting question. I wonder, yeah, because if you've focused them to the same kind of a long track resolution, at least the long track they'd be comparable. The cross track, there's still the HF is going to be much broader.
Right.
It's going to be, that would be interesting to look at that kind of sub-deposit roughness, because that will also look different between the two different frequencies. So
yeah. And then a second question, if I might. I mean, we've discussed this offline in a bunch of, but looking at that thing of the pond feature that you have up there, example, implies that you're not draping, right? That there's something that's redistributing this material to a constant equipotential surface. It's not a pure drape and softening of the topography. I mean, the alternative hypothesis you could have, and I'm not sure about the literature for it, everything we're seeing is fluff. And then the pond is a thermal anomaly that centered it all.
Yeah, it could be. So the issue with the sintering is there was a study done last year where sintering rates on Europa, for Europa surface temperatures, you have to have a very large thermal anomaly near the surface to sinter it to the point where it looks that different. Like sintering is not expected to, or at least densification is not expected to play a major role. According to this one study I read last week, sintering is not expected to, or densification due to sintering is not expected to play a major role anywhere on Europa's surface. It's just too cold and it hasn't been there long enough.
Okay, but you still need some kind of process to level things out if the pond represents an alteration of pre-existing topography.
So, okay, maybe I'm misunderstanding the.
So if you're just filtering stuff down from above, it's
Yeah.
going to drape onto the pre-existing topography, and eventually, I mean, they'll start smoothing out. There'll be some kind of smoothing kernel that fall over the topography. But it seemed pretty abrupt in that one image we have of the one thing. Galileo had big data issues, so there isn't a lot of imagery of Galileo. But somehow you have to move things from the peaks into the valleys, it seems, in order to get that
Sure.
smooth surface. So I don't know what is the more improbable hypothesis, that somehow you've had some kind of large-scale densification process and you've removed that topography, or you have stuff that is moving around on top of the deposit.
I don't know about. I don't know how much mass wasting would be active on ridge terrain, but maybe it is the case that things just flow downhill. I don't know if it's enough to, if the gravitational potential from the top of these things to the bottom, but there's no wind. Like, what's going to move it? It have to be on a pre-existing slope.
Seems to be a problem. And then as the topography gets smaller and smaller and smaller, there's less gravitational potential energy to drive the process. Yeah. So it seems hard to get rid of it altogether. So maybe it's just an imaging glitch, but yeah.
Maybe those things are just incredibly.
Yeah. Hey Duncan, have you thought about the electrostatics of that? Because when things get that fluffy and that cold, the electrostatics of those particles, and as they accumulate, the changing electrostatics is going to be a really, really interesting particle flow environment.
That's a good point, especially with all that radiation and stuff going on.
No, it's a super interesting question. I never thought about. I always just assumed it would just fill in the low points first, but actually, there's no reason it would.
Looks like Natalie has a question as well.
Yes, I guess it was kind of related to what Duncan brought up. I don't know if maybe you can put up the image that showed the two features where it looked like there were plumes. I was kind of curious, if you considered plumes to be the hypothesis of last resort, what other explanations might there be for those features that we?
Okay. Let's get out of this and go this way. So these two here.
Yeah.
Yeah, they're thrown around a lot as general cryovolcanic features. Now, what that means, if it's like a cryolava versus some kind of fallback deposit, I don't think there's much evidence to dissuade them one way or the other. I know there's some work that's being done on specifically this kind of pondy thing as a cryomagma out of a group in France, but I still haven't wrapped my head around it completely. And they were actually able to go through and kind of map or pseudo map the position of these ridges as it crosses underneath and kind of get effusivity rates if you wanted to fill those in and build up on top of it. So.
And so I guess with the crater ejecta, you can kind of see it here, that tends to be really bright, yeah?
Yeah, I think crater ejecta usually tends to be brighter than what's seen in kind of this area and these low albedo ones down there.
Yeah, that's super weird.
But yeah, as to what else it could be, both of these have also been hypothesized to just be effusive cryovolcanism features, flows or whatnot.
Cool. We can address Cyril's other question. Says, as for current knowledge, what constraints do we have for plume deposit thickness?
Yeah, probably not much. As I mentioned, like there's that one study from the group in France. I don't think it's actually published yet. I think it was just in an archive. I just saw it during a seminar once where they actually went through and kind of tried to make a DTM of this area and track these kind of ridges as they go through. So like say this ridge is that ridge, what does it look like? And then take a cross section through, okay, what is the actual thickness of these things? I don't remember exactly what their numbers were, but I think that's one of the, that's the only one I've seen actually trying to do it, trying to get at that subsurface topography under these things. Maybe there's more, I just haven't found them yet.
Fair enough. Any other questions today? Awesome. Well, this was a really cool discussion hour. I enjoyed hearing about it. Thanks so much, Kirk.
No, thanks everyone for coming. Lots of
Awesome.
fun.
We'll see you all next week.